4.3 Day 8 notes. We're looking at graphs of exponential functions. So for the first example, we're just going to sketch a graph for y equals 2 to the x. So some things you should note when we go to graph this. The a value would definitely be 1, like the coefficient on the actual function itself. The a value would be 1. And then the b value is that number 2. So the b value is 2. This is definitely exponential growth. So we could easily make a sketch of a function showing exponential growth, and then the y-intercept would be there at 1. And so what I want to focus on then is this line that it will never touch. So if you remember, those are called asymptotes. The line that it gets really close to but it never touches. So exponential functions have these in some form or fashion. So that's an asymptote. So that's like an imaginary line that the graph approaches but it doesn't touch. So this is the part of the graph that approaches it, right? I just circled it here. So the part that is going down towards this line, getting ever closer, that's the part that approaches that line. Not this part. This part's kind of just blowing up, going to infinity. So the line here, in this case, this would be y equals 0. So the asymptote would be y equals 0. So what does that mean? Essentially it means that you could never plug a number in for x, and the output, like the answer for this, would be 0. You could never plug a number in for x that would give you an output of 0. Think about that. Even if you plug in 0 for x, 2 to the 0 is 1. So just like you can never actually get negative answers here, like it never goes below the x-axis, you can never get negative answers. You can also never get 0 as an output for y. So that's why y equals 0. That ends up being an asymptote graphically. Okay, so in general, for our exponential functions, y equals a b to the x. If a is greater than 0, so if a is positive, b is greater than 1, so you have exponential growth, which is essentially exactly what this is modeling. In this scenario, you know it would be an increasing function, like exponential growth. If you have a positive a value, but then the b value is a fraction between 0 and 1, that means it's a decreasing function, so that was exponential decay. Okay, example 2. I'm going to start out with just a general sketch. I'm going to put a few graphs on here. So try to follow this one closely. Here's graph A. It's definitely exponential growth. It's above the x-axis somewhere. And then graph B, add that in here. That's going to be graph B. So it's a lot like A, but it's a little lower. Its y-intercept's definitely below it. And then I got graph C. Actually has the same y-intercept as B does, but notice it's a little flatter, right? It's not increasing quite as fast. It started above it back here, they cross here at the y-intercept, and then it's staying below B. And then graph D, that's actually exponential decay, but it crosses here with B and C. And then graph E is another exponential decay. It crosses with B, C, and D as well, and it goes below D. And then graph F, it's kind of all alone down here. Yeah, below the x-axis there you have graph F. So see if you can make that sketch. And then I'm going to ask you to match these correctly to their function. So here are my functions. y equals 3 times 0.7 to the x, 0.8 to the x, 1.2 to the x, 1.4 to the x, 4, 1.2 to the x, negative 3, 0.7 to the x. So if you think you know enough to do this right now on your own, please go ahead, just pause the video and try to match these up as best you can without me going through it and giving you the answers. So go ahead and try it on your own. Okay, so a couple things you should notice. The first special thing that sticks out in my mind is that these four graphs, B, C, D, and E, all intersect at the same place at the y-intercept. So if they all have the same y-intercept, that means they all should have the same a value. And if you notice, there's four graphs over here that have the same a value. So they all must intersect here at 3, like the y-intercept. Okay, so that's the first thing I notice. So B, C, D, and E, they all have the same y-intercept. Okay, and then how do we differentiate between those four? Well, 2 of them are actually exponential growth. The other 2 are actually exponential decay. So B and C are increasing. Those are exponential growth. And D and E are decreasing. Those 2 are exponential decay. So that would help us rule out a couple when we're actually matching these up. Okay, so and then for the 2 that are exponential growth, for the 2 that are increasing, B increases faster than C. If you look in the quadrant 1 here, B goes up faster than C does. So it's got to have a higher B value, right? It's got to have a higher growth factor. So of these 4 graphs, we know they all have the same y-intercept. The 2 that are increasing, the 2 that are exponential growth, would be right here, 1.2 to the x and 1.4 to the x. So B must be this 1.4 to the x because it's increasing faster than C. And that leaves us with C as 1.2 to the x. So those 2 are done. And then between D and E, so D and E are both decreasing. They must have the same A value. Which one has a lower or a higher B value? Well, for sure, E is decreasing more. Like it's decreasing faster than D. So E, if you notice, like it drops below it, it's a lot sharper curve here. So E is decreasing faster than D. D is a little flatter. So if you're decreasing faster, that means you have a smaller number for your B value. So E would be this one, the first one, 0.7 to the x, and then D would be the 0.8 to the x. Okay, the last 2 should be relatively obvious to you. For starters, there's only one that has a positive A value left, and notice it's higher than all the other A values. So that should be graph A, and there's only one with a negative. So that was my last 2 notes here. F has a negative A value, right? It crosses the y-intercept below the x-axis, so it's got to have a negative A value. So that doesn't leave us much choice for F. And then the only one that's left should truly be A, because it has a larger y-intercept than all the other graphs. So there you have it. I hope you're able to follow that one and do it on your own also. Last slide for these notes, we're going to talk about horizontal asymptotes, which are really just horizontal lines. So that's always y equals some value. So we're going to call it y equals k for our horizontal asymptotes. Okay, the first case I want to look at. So we say f of x, and this arrow means approaches. So f of x approaches k. As x approaches, well, it's going to be either negative infinity or positive infinity. I'm going to look at both cases. So the outputs approach k, or like the y values approach k, as the inputs approach negative infinity. That's like y approaches k as x approaches negative infinity. So let's talk about exponential functions that way. So here's your graph. Here's a general sketch of exponential growth. And negative infinity is this end. So the x values, as they go to negative infinity, what is this graph doing? What is this function doing? Well, it's going down. It's getting lower and lower and lower. But there's some value that it'll never reach, right? Before it was 0. So whatever this k value is, and it could be 0, whatever it is, the k value, it'll never cross that line. So that's what makes an asymptote there. And the same thing holds if you want to go to positive infinity. So this one I'll do for positive infinity. So let me erase this here. There we go. F of x approaches k as x goes to positive infinity. So the same type of setup. Now let's look at exponential decay. So as the x values go to infinity, like this graph, what's it doing? Well, it's getting lower and lower and lower. So whatever this k value is, as this thing goes to infinity, that's the line that it approaches, but it never touches. And again, this could be 0. K could definitely be 0. That's a common one. So like it approaches the actual x-axis. But I need to illustrate this one, so I drew k right here. So example 3, here's a function, y equals 6 times 1.4 to the t. So we can easily make the sketch of this graph. Right, just drew axes. I know the a value is 6, so the y-intercept 6, and this is exponential growth, so it looks like this. So now I just want to look as t goes to negative infinity. So t, that would be like the t-axis instead of the x-axis. So that's like this. That's the t-axis. As t goes to negative infinity, so this direction, what does the graph go to? So definitely the outputs are approaching the t-axis here. So I would say that y goes to 0, which in this case, again, our horizontal asymptote would just be y equals 0. And then for this graph, how about we go the other way? So as t goes to positive infinity, what does y go to? Well, t moving positive infinity, it's not like approaching a line, right? It's actually just kind of blowing up. This graph just gets bigger and bigger and bigger. So it just goes up to positive infinity. So this goes back to in behavior. We actually learned a lot about this in Algebra 2. In this direction, the t values get bigger, the graph goes to infinity. In this direction, the t values get smaller, the graph goes to this line, y equals 0. Alright, final example for these notes. Example 4, y equals 6 times 1.4 to the t plus 3. So if you'll notice, this is the exact same graph as before, except that plus 3, what is that going to do? Since it's outside, it's not with the variable, that's going to shift the graph up 3 units. So you can essentially take the same exact graph, same exact sketch, move everything up 3 units. And my overall question is, what is that going to do to like the horizontal asymptote? So I'm just going to take this graph and go up 3 units. So the y-intercept is no longer 6. I know the a value is 6, but then the plus 3 shifts everything up 3. So that way, now it crosses here at 9. So what does that do to my horizontal asymptote? Well, if the entire graph got shifted up 3 units, then that imaginary line that it'll never touch, that could shift it up 3 units as well. So now, my horizontal asymptote is not y equals 0, but add 3 to it, it's y equals 3. So what can we say as t goes to negative infinity in this case? So as the graph goes to negative infinity, what does it get really close to? What does it approach? Well, it's no longer this line, right? It's the same line that you got shifted up 3 units. So now y approaches 3. So as t goes to negative infinity, the y values get really close to 3. And then as t goes to positive infinity, so this way, on the t-axis, as that goes to positive infinity, what's the graph doing? Well, you'll notice it's kind of blowing up. It's getting bigger and bigger and bigger. It's not really approaching anything. So it's just going off to infinity. So that one, we say y goes to infinity. Alright, so that's a little bit of a preview about end behavior and then what the graph's doing at the ends. Like on the t-axis here, positive infinity, negative infinity, and then what kind of asymptotes exponential functions have. So that's all for these notes. I'll see you in class.